Hi, I'm Scott Leslie, and I'm here with John Amrine. John is a significant contributor to SAS Global Forum, including being the conference chair in 2017. We'll be watching his pre-recorded presentation entitled Modeling Causal Effects Using SAS Stat. Once the recording completes, John will be answering questions that you submit in the YouTube chat window. So let's get started.
Welcome to Modeling Causal Effects Using SAS Stat. My name is John Amrine. I am Vice President, Managing Director of McDougall Scientific Limited. We are a contract research organization providing statistical and other data-related services to the biotech, pharmaceutical, and medical device research organizations. We are headquartered in Toronto, Ontario, Canada, and we are a member of the Alimentive family of companies. In today's presentation, I will describe a few concepts of causality, including a reminder that causation differs from correlation. I'll explain counterfactual thinking, which is key to understanding causal analyses. I'll touch on potential outcomes, and finally, a definition of causality. The concepts will lay a basis for the methods that we will use for causal analyses, and if those are done properly, will allow you to declare cause and effect. This presentation focuses on causal modeling that models the outcome of interest. Let's get started with a few concepts of causality. We'll compare causation to correlation, emphasize our focus on how data are generated, and describe counterfactuals and potential outcomes. We have all heard the saying that correlation is not causation. In a broad sense, correlation or association is any relationship between two quantities or variables. Whereas correlation describes how quantities vary together, causation is a stronger statement, implying that one variable induces the value of the other. Correlations can be quantified through observation. For example, measuring a child's height and weight. Causation, on the other hand, can only be quantified by intervening or changing one variable to see what happens to the other. In the height and weight example, we would need to change a child's height and observe what happens to weight. It is important to keep in mind that because we have to intervene to change the value of one of the variables, exposing cause and effect implies that we need an understanding of the data generation process, rather than simply observing the end results. Counterfactual thinking is the ability to imagine a world that has never been and really can never be, or at least a world that is contrary to that which exists. For example, stating that had I not eaten popcorn, I would not have gained weight implies an alternative world in which popcorn is not eaten and weight is not gained. That world can never be once the popcorn has been eaten. Only one path can be taken. The fundamental problem of causality is that at an individual level, a person or an experimental unit, only one world can exist. The alternative world is impossible once the other becomes fact. You cannot reverse time and not eat the popcorn once it's been eaten. But counterfactual thinking allows us to consider the alternative. Although unit-level causality cannot be quantified, population causal effects can be when certain conditions are met. And in this presentation, we will learn those conditions and how to estimate population-level causal effects. Potential outcomes is a concept that organizes and establishes a formal framework for counterfactual thinking. Potential outcomes are events that are possible under alternative paths. For example, an intervention of interest might be eating popcorn, and the outcome of interest is weight gain. In that example, we have two possible paths. We eat the popcorn or we don't. And we have two potential outcomes, weight gain or no weight gain. The table on this slide shows n individuals in an experiment. We have y sub 1 and in parentheses another 1 in that top left cell. That's in the treatment outcome column. That refers to individual 1 is the sub 1, and in parentheses, the 1 means that this individual realized or was assigned to the treatment. That is, they ate the popcorn. Any of the outcomes that were measured for an individual are in black, and the one that was not measured is in red. So for unit 1, the one in black was the treatment outcome. This individual ate the popcorn. And the Y sub 1, 0 is red because that person did not eat the popcorn. Only one of these potential outcomes can be observed for each individual. So the final column, causal effect, are in red for each individual because we cannot calculate or measure the causal effect at the individual level. However, the bottom row shows that if we compute the mean for each column, the treatment and the no treatment columns, we can compute a causal effect at the population level by differencing the means. To do this, we must meet certain conditions. But that quantity, the causal effect at the population level, is called the average treatment effect, ATE, or the average causal effect, ACE. We will make the following assumptions for the cause analyses throughout this presentation. These are the conditions that we have to meet, and it's kind of a handful, but these are important. The first one is positivity. And on this slide, we show above baseline positivity states that at an individual, they have a positive probability of receiving each of the treatment assignments, 0 or 1. Without positivity, it doesn't make to consider potential outcomes. If an individual has no chance of receiving one of the treatments, then there is no causal effect of treatment for that individual. So each individual must have a chance of getting each treatment. The next one is called SUTVA, S-U-T-V-A, which stands for the Stable Unit Treatment Value Assumption. Assignment assumption, stable unit treatment value assignment assumption. It's a mouthful. This assumption states that a unit's potential outcome is not affected by another unit's treatment assignment. So it's the treatment outcome for the individual compared to the treatment assignment for another individual, that the assignment of the other individual does not affect the first unit's outcome. We could probably spend at least a half an hour getting into the details of this assumption alone. But to suffice it to say that SUTVA is necessary for causal effect to be defined at the individual level. Sometimes it might be necessary to increase the number of potential outcomes to satisfy SUTVA, but that's a complication beyond the scope of this presentation. The third assumption is consistency. A unit's potential outcome under a treatment is its realized outcome. Consistency allows us to use observed outcomes to estimate causal effects. Simply, this means that if unit 2 here is assigned to no treatment, 0, and the potential outcome is quantified at baseline, that potential outcome is what we will observe after we measure the outcome. The last assumption is ignorability, and this one comes into play in many places in causal effects, even in randomized controlled trials, where I spend a lot of my time. Ignorability says that given an appropriate set of confounders, represented by the large X on the slide, a unit's mechanism for being assigned to treatment can be ignored. You see above the X, I have randomization and self-selection. Randomization is one way of assigning a unit to a treatment, and self-selection is another. We could randomly assign individuals to eat popcorn or not, or we allow them to choose to do so. And ignorability says that given a set of confounders that conditioned on them, that we can ignore whether it's randomization or self-selection. This is also called exchangeability. And formally on the slide, you see that we say the potential outcomes are independent of the treatment conditioned on the set of confounders. Now, there are several methods to control confounders. via randomization, propensity scores, stratification. We'll see how to control for confounders in our structural causal models. Okay, finally, a definition of causality. On this slide, we represent an outcome. O is the effect and C is the cause or the treatment. An outcome O causally depends on a prior event, C, if and only if the occurrence of C implies that O will occur, and the absence of C implies that O will not occur. So if we have C, we have O. If we don't have C, we don't have O. However, the world is not so simple, and there's usually a sequence of events that must occur before the outcome is realized. And we call this a chain of causal dependence or a mechanism. And each event in that sequence is causally depends on the previous event. Okay, we're ready to discuss some methods of causal analyses. We will focus on modeling the outcome, although you can also model the treatment using propensity scores. And first, we'll talk about the gold standard randomized controlled trials. Randomized controlled trials, or RCTs, have been the gold standard to estimate causal effects. They are a broad class of experimental designs, usually in which humans are the experimental unit. They're common in medical and drug development studies. The C in RCT stands for a control group, against which a treatment group or intervention, as shown in the slide, is compared. The control group does not receive the treatment or the intervention under study. The R in RCT indicates randomization. The study participants are randomly assigned to the treatment or the control group. They do not self-select. This randomization eliminates the ability of the participants to choose whether they receive the treatment or not. And this is done to control the confounders that are so important to ignorability that we talked about in our assumptions. Confounders influence selection of a treatment and are also related to the outcome. If individuals with a specific profile are more likely to choose one treatment over the other, then the distribution of the variables in that profile may be unbalanced from one treatment group to the other. That induces some confounding, and we have to control for that when we conduct our analyses in order to declare causality. Randomization ensures that balance so that the control is taken place at the beginning of the experiment. The difference between the outcome of interest in an RCT is our estimate of the ACE or ATE, the average causal effect or average treatment effect. Now, we often do not have the luxury of working with data generated in RCTs. So how do we account for confounding in observational studies? One way is through propensity scores. Propensity scores are used often when randomization is not possible. In retrospective studies, using data that are collected for some other reason, such as medical records, customer transactions, or utility consumption. Studies analyzing retrospective data have no opportunity to randomly assign individuals to treatment. However, the observational data has variables we need to conduct an analysis of interest. Propensity scores offer a way to isolate the cause of interest from the confounding factors when randomization was not used. The propensity scores are probabilities of being assigned to a treatment group. In this case, on the slide, the treatment group is labeled as cases, and the no treatment group is labeled as controls. So the propensity score is the probability of being a case. They are estimated usually by logistic regression by specifying the binary treatment indicator as the response and the covariates as predictors. The covariates are the confounding factors that we need to control for. Once we have those propensity scores, we can conduct analyses in different ways. We can match the treatment and control observations by similar propensity score. That's depicted on the left of this slide, where we have a case and a control with similar propensity scores that will be matched, and we conduct a matched pairs analysis. Another alternative is to compute weights and conduct a weighted analysis. On the right side of this slide, we see the unweighted comparison of the distributions of age between cases and control. Once we weight using the propensity scores, those distributions are very similar, and we have therefore taken account of the confounder age. The PS match procedure in SAS stat provides methods of weighting, stratification, and matching. The objective is to achieve a balance of confounding distributions across treatment groups. PROC PS match assesses covariant balance by comparing the distributions as you see on the right in this slide. But you must specify the set of X, the confounders that you use to estimate the propensity scores. PROC PS match will not help you identify the appropriate set of confounders, nor will it tell you if you have used a good set of confounders. We will see how to use PROC CAUSALGRAPH to help us with that problem. So moving on to structural causal models, this slide shows the topics that we will discuss. We're going to get into graphical models called DAGs, directed acyclic graphs. We will describe a few different constructs for those graphs. We'll discuss the concept of blocking, which is a graphing terminology for controlling variables. We will link graph models to statistical analyses through deseparation, and we will show you how to use PROC CAUSALGRAPH to find the set of confounders you need to control for, and then do the analyses in CausalMed and CausalTRT. There are other topics that fall under structural causal models, like structural equation models and Bayesian networks. I will mention those, but we won't get into them in detail. And you can use other SAS stat regression procedures to conduct causal analyses, but doing so is beyond the scope of this presentation. A graphical model is a visualization of relationships between variables. Variables are represented by nodes and relationships by connecting edges or arcs. Depending on the type of model, connectors can be single or double-headed arrows. Connectors can begin and end at the same node. The absence of a connector between two nodes is as important as a connector between two nodes. The absence indicates that those two variables represented by those nodes are not related, they're not dependent, or they are independent. This slide shows a directed acyclic graph, or a DAG. It's a special kind of graphical model. Letters A through G represent the nodes. A graph is directed because each arc between two nodes is uniquely directed, that is, it's a single-headed arrow. The graph is acyclic because once you leave a node, you cannot get back to it. There are no arrows going backwards. The terms on the slide are familiar terms, and they're meant to allow us to talk about the different nodes and their relations to each other. Focusing on the node in the center, node A, nodes B and C are node A's parents because they precede node A. B, C, and F are the ancestors. As a group, they precede node A. Nodes D and E are children nodes of node A, and D, E, and H are the descendants. Two nodes that have a common child, like node D is a child of nodes A and G, make nodes A and G spouses. We need to talk about three graph constructs for causal analyses. This is the same graph we just saw, but it's in triplicate. We've relabeled nodes A and O. Let me try that again. We have relabeled node A to O as the outcome, and we have labeled one of the other nodes T for treatment. We have also added node M as a mediator. There are three basic constructs. On the left, we have a causal path, is a directed path from cause to outcome. You note that there can be a mediator, node M, in between the treatment and the outcome. A confounding node, like node C in the middle, is a parent of both the cause of interest, node T, and the outcome, O. A collider node, like node E, is a child of both the treatment and the outcome. This construct is called endogenous selection. The cause of interest, or treatment T, and the outcome O are associated in the causal and confounding constructs. They are not associated via a collider. To isolate the causal effect of interest, T, we need to dissociate the treatment and outcome from all confounding paths. At the same time, we must not dissociate the treatment and outcome in the causal path, nor should we introduce a confounding association via collider. More about that on this slide. To dissociate two nodes that have a natural association via a confounding path, we must block that path. Later, we will explain that when we say blocking a path, we are adjusting for or conditioning on the variable represented by that node. So given our three constructs, we do not want to block the path TMO because this is the cause of interest. If we mistakenly do block this path, then our resulting bias is called over-control bias. In the middle, we do want to block the path TCO to dissociate O from T via the confounder C. Doing so will isolate the causal path of interest in our analysis. If we mistakenly do not block a confounding path, then our analysis will suffer confounding bias. We do not want to block the TEO path, the collider path, because right now there is no association between T and O in this path. If we do block this path, then we will create a confounding association and introduce what's called endogenous selection bias. So for our causal analyses, we do not block the causal path. We do block confounding paths, and we do not block collider paths. Now, a little more about this endogenous selection bias, because it can be confusing and can be counterintuitive. So a very small, quick example might help. Consider an outcome of risk status for coronary heart disease, represented by D for disease on the slide. One of the measured variables is quality of life, QOL, represented by Q on the slide. Quality of life is often measured through a questionnaire. The outcome of interest, disease, causes below normal quality of life. So we have an arrow from D to Q. A CHD treatment, or treatment for coronary heart disease, represented by T, is under study and is expected to lower the risk of coronary heart disease and increase the quality of life, perhaps by returning patients to normal levels of daily activities. So we have arrows directed paths from T to both D and to Q on our diagram. T is the treatment node, D is the disease, and Q is the quality of life. The objective of this study is to estimate the direct effect of treatment on coronary heart disease risk. Now let's focus on the quality of life. If we do not know an individual's quality of life level, then we have no information regarding the treatment status or the risk of heart disease. However, suppose we happen to know that quality of life is very low. Then we know that it is more likely the patient is not receiving the treatment, assuming the treatment works, and that this disease risk is high because the quality of life is low. Therefore, if we were to block this path and set a level of quality of life, then we are getting information about both the treatment and the disease, and we are inducing an association that did not otherwise exist. And for that reason, we do not block collider paths. Okay, we've talked about graphing models and graphs and constructs and models. How does that get us to a statistical analysis? The link between graphs and analyses is a concept called deseparation. Now, blocking is a graphical term, and when we talk about adjusting or controlling or conditioning on, those are statistical modeling terms. The two are connected through this concept of deseparation. And it's time now to conduct our analysis, and we've been relying on graphical models to visualize the data generation process and the variable dependencies. But the graphical models are not themselves analyses. We need statistical analytical methods to conduct the analysis and estimate our ATE or ACE. And to make the transition, it's helpful to understand this deseparation. And the D stands for directional. And there are two nodes are deseparated when there is no connecting path between them. If a connecting path exists between two nodes, they are called deconnected. Now, in graphical terms, two nodes are deseparated when every path between them has been blocked. Between two nodes, they are deconnected if there is at least one path between them that remains unblocked. The transition to statistical methods, and you can read just about any of Judea Pearl's books or papers on causal models and graphical models to learn more about this. If two nodes are deseparated, then the variables between them are definitely independent. So deseparated means that they are independent. If two nodes are deconnected, then the variables they represent are possibly or likely dependent on each other. And we block paths via conditioning or adjusting for variables whose nodes are confounding paths or by the presence of colliders. PROC causal graphs tells us which nodes to condition on or to adjust for. And it identifies an adjustment set or adjustment sets. It also identifies which nodes should never be included in an adjustment set. Now, a note of caution before we get into our causal graph procedures and our analyses, that causal graphs are comprised of nodes that represent variables. The graphs do not consider the shape of relationships between those variables or the distributions of those variables. When transitioning to causal analyses from the graphs, it is important to keep this in mind, especially if you're using parametric methods like regression. Ideally, we would use non-parametric methods, but that's not always possible. To demonstrate causal analyses, we're going to use a data set called HEART, which is in your SAS help library. The data set contains 5,209 adults who participated in the Framingham Heart Study. You can find that online by searching on Framingham Heart Study. sashelp.heart was used by an author, Fechner, in 2018 in a pharma user group paper in Europe using the PS match procedure. So I encourage you to look up that paper, 2018 pharma user group in Europe. She used the PS match procedure to analyze these data for causal analyses. Between that paper and my paper, you could compare the two different methods and see which one you like or better or which one you prefer. Now, the Framingham Heart Study itself was initiated in 1948 in Framingham, Massachusetts, to study risk factors associated with coronary heart disease. The heart data set in the SAS Help library is a subset of the full data set and includes 17 variables. Suppose the graph in this slide represents our belief of these relationships between the variables. And I have to, for full transparency, this is my depiction. No subject matter experts were involved in this. So this is for illustration purposes. And suppose we're interested in estimating a causal relationship between assumed risk factors in coronary heart disease. And those risk factors might be weight, metropolitan relative weight, which is an alternative to BMI, cholesterol, smoking, and age. For each of these, we can use PROC causal graph to tell us which covariates need to be included in adjustment set to analyze the risk factors to coronary heart disease. And these are some of the variables in the data set: age at death, age at start, These are integers in years. The age at which heart disease was diagnosed, blood pressure status, cholesterol status. Cholesterol is a continuous cause of death, which we won't need that for our analyses. Diastolic blood pressure, height, MRW, sex, smoking status, and so forth. Excuse me. Okay, a couple preliminary steps to prepare our data. In this data step, I divided cholesterol by 10 to make it less granular. So when we do an analysis of cholesterol, our estimates will be with respect to a 10-unit increase in cholesterol. I chose a time point for heart disease status, 5 years, within 5 years. So I just created a binary indicator if the age of diagnosis is in between the age at the start and 5 years later. Blood pressure status, I combined it so that it's binary, optimal, or normal. And then smoking status, I combined it, collapsed the levels so it's also binary, a non-smoker and a smoker. A quick PROC freak on our heart disease status shows that we have just about 200 individuals with heart disease in our new data set. The causal graph procedure in SAS stat software identifies nodes which must be or can be blocked to isolate a causal path of interest. When a causal path can be isolated, that is, all the confounding factors can be blocked, we say that the causal path has been identified. You specify your directed acyclic graph on the model statement. We'll see how to do that. And you identify the causal path of interest on the identify statement. If any of the nodes represent variables that are or will be unmeasured, you specify them on the unmeasured statement. Unmeasured nodes cannot be blocked, so it's important to let PROC CAUSALGRAPH know which of those nodes cannot be blocked. And here's our PROC CAUSALGRAPH statement or step. Note that there's no data equals option on the PROC statement. CAUSALGRAPH does not require any data. On the model statement, we specify a model name or label, and then we construct our graph. We translate our graph from the picture that we had mapped out on a PowerPoint slide or on paper into parts of the statement. Each link between nodes is separated by a comma. For example, height, and then an arrow to the two variables that are children of height, weight, and MRW. And we do this on and on until we have mapped out our entire DAG. You can specify multiple nodes on the left or the right of the arrow. It's important to separate them by commas and only one semicolon at the end of the statement. In our graph, we had 3 unmeasured nodes or variables. They were represented by the ovals on the graph. They are nutrition, activity, and genetics. And in this case, the causal path of interest is cholesterol and its impact on CHD. In the output, the first 2 tables, you should review these to make sure that your model was received or you coded it as you intended. And the variables in the model, we list 11 measured variables and 3 that are unmeasured. In the graphical model summary, we get a count of the number of nodes, number of edges. We have 1 treatment, 1 outcome, and again, 11 measured and 3 unmeasured variables. And then the next table is the output that we're looking for. It is the adjustment sets. They are sorted according to the size of the adjustment set, and we are told whether it is a minimal adjustment set, yes or no. In this particular model for cholesterol's impact on disease, there are 92 different adjustment sets that are possible. You should take note of any nodes that don't appear in any adjustment set, such as blood pressure status. Now, minimal adjustment sets are not the smallest adjustment set. Minimal adjustment sets are those for which there is no subset of that adjustment set that is also an adjustment set. If you want to display just the minimal adjustment sets, then you put the minimal option on the PROC causal graph statement. You can specify a max size for an adjustment sets that are displayed in the table by using the max size equals n option. And if you just want the smallest one, max size equals min. By default, PROC causal graph is only going to list 100 adjustment sets, and you can override this default, raise it or lower it using an option called max list, and that is also on the PROC causal graph statement. If there is an adjustment set of particular interest to you, you can specify that adjustment set on the test ID statement. If we're interested to see if we can add blood pressure status to our smallest adjustment set, which was MRW and smoking, then on the test ID statement, we just add BP underscore status and test that. You will only get the table for that one adjustment set that's on the test ID statement. You will not get the default table. Now remember our graph, blood pressure status is a mediator between cholesterol and CHD, and we said we should not block causal paths. And indeed, PROC causal graph tells us that that is not a valid adjustment set. So we cannot use blood pressure status in combination with MRW and smoking to adjust as confounders. Okay, so for all of our causal factors of interest, we put our PROC causal graph inside a small macro, so it loops through, and we loop through weight, metropolitan weight, cholesterol, smoking, and age. Note that we specified the minimal option on the PROC statement so that we only get the minimal adjustment sets for each of those. And this table shows the minimal adjustment sets for those different factors. For MRW, the top row, cholesterol, and my slide's too small. I can't see what that says. There's two variables for MRW twice. Weight only has one possible adjustment set. Cholesterol, there's 3. MRW and smoking, that's the one column. And for age, we don't need to adjust at all. No confounding factors need to be adjusted for. Smoking, there's only 1. So this tells us in our analyses which variables we should control for in our model. Now, before we do that modeling, a couple other possibilities, modeling choices. One is structural equation models. Very similar to what we're doing here with DAGs and what we will do with CAUSALMED, CAUSALTRT. But in structural equation models, if you're familiar with those, you know that we estimate parameters for every path in the model. So it's quite complicated. Also, there are distributional assumptions on these variables. They all have to be distributed normally. But if you are able to meet the conditions for cause and effect that we talked about with structural equation models, then that is a viable option. Another modeling option, which I like very much, is Bayesian networks. Bayesian networks also rely on graphical models, but through recursive estimation using Bayes' theorem, we estimate probability distributions for each node. And for our outcome, we get a final probability distribution for estimating probable outcomes values for that outcome node. These models are quite powerful. They can get started because it's Bayes' theorem with subject matter expertise. You don't require data. And they can be operationalized, and they are common in artificial intelligence applications. Okay, let's get into the CAUSALMED procedure. We're now ready to conduct our causal analyses. The CAUSALMED procedure is in our toolbox of choices for our analytical methods. PROC CAUSALMED conducts mediation analyses for causal interpretation. Recall our simple graph with model treatment, our graph model, sorry, with treatment, mediator, outcome, and confounder nodes. An edge connecting treatment to outcome has been added. And CAUSALMED fits generalized linear models for measurement scales listed in this slide. So for treatment, we can have binary and continuously measured treatments. The mediator can be binary or continuous, and CAUSALMED supports binary and normal distributions. The confounders can be categorical or continuous, and the outcome can be binary, continuous, or count. And the distributions supported are binary, negative binomial, Poisson, and normal distribution. The mediator and outcome nodes, which will be response variables in the fitted model, have distributional assumptions, and they're shown here as we just described. Here's the syntax for CAUSALMED procedure. These are selected statements, not all of them. And you must specify one and only one for each of the treatment, mediator, and outcome variables. But you can specify multiple confounders, and you can specify their interactions. You specify categorical variables on the class statement as you do in other SAS stat procedures. On the model statement, the outcome variable, which will be CHD 5YR, is specified to the left of the equal sign. On the class statement, we specify blood pressure status. And we have our ref equals options as we do in other SAS stat procedures. And CHD5YR, that's the disease at 5 years. The reference level is 0 or no disease. On the model statement, we specify the outcome. And to the right of the equal sign, we specify our causal effect of interest, cholesterol, and blood pressure status, which is the mediator. And then the mediator statement, we specify the mediator itself is dependent on cholesterol, the treatment. So we are just coding the small graph that we had. Now, PROC CAUSALGRAPH told us that we had to control for two confounders, MRW and smoking. So we specify those on the COVAR statement. And on the evaluate statement, we can specify units or a covariate of interest, and we can put it in the units that we're looking for. I was trying to think of this is not uncommon or not unlike the LS mean statement in other SAS stat procedures where we use at and then a certain level. So we're looking at what's the impact of smoking, 60 cigarettes, which would be 3 packs. The output from that step starts with the model information table. Review this information table to make sure the model was coded as you had intended. We could have specified a distribution or a link function with dist equals or link equals options on the model statement. Again, not unlike other SAS stat modeling procedures. Because we did not, SAS will use the binary distribution with the logit link if the outcome variable is listed in the class statement. If the outcome variable is not listed in the class statement, CAUSALMED procedure defaults to the normal distribution with the identity link function. Review the response profile and the mediator profile to ensure that the counts for the different levels of the two binary variables are what you expect. For binary variables, we also get notes indicating the levels that logistic regression will model. And we set the levels with the ref equals option on the class statement for these two variables. Now, the summary of effects table represents a lot of information. It presents a lot of information. And to interpret these results, we should understand the quantities that are being estimated. So we're going to spend a little bit of time defining the quantities that are in this table, such as the controlled direct effect, the natural direct effect, and the natural indirect effect. Because we have a binary outcome, we get both the odds ratio and the relative risk. But let's talk about these different decompositions of the effect. And I'll use our little graph that we've been using to help us visualize what's happening. And the dash in the middle of this slide is a subtraction sign. So we're subtracting one quantity from another. The total effect is the difference in outcome between treatment and control values. Because the treatment has a causal relationship with the mediator, we distinguish the value of the mediator with when treatment is 0 versus 1. M sub t is the value of the mediator when treatment is level t. So we have M sub 1 and M sub 0. And M sub 1 on the left is the mediator when treatment is at level 1, that is treated. And M sub 0 is when the treatment value is at level 0, untreated. Note that we are not intervening on the mediator. Rather, it takes the value that is induced by the treatment itself, and we're subtracting these two quantities. So this is the total effect. We can decompose the total effect into direct and indirect effects. Direct effects can be controlled by intervening on the mediator and setting it to a specific value. By doing so, the indirect effect, mediator to the outcome, is the same in both summands, and the difference is only the direct effect, which is from treatment to outcome itself, represented by the solid line. So we're not saying in this slide, we're not saying which value we're setting the mediator at, but we're saying we can do so. So the natural direct effect is a difference in the outcome between treatment levels with natural mediation. That is, there is no treatment. The natural direct effect is the control direct effect when we set the mediator at the value it obtains when the treatment is at its control value. So even when treatment is 1 on the left, the mediator is set at its level when treatment is 0. So the mediator value is both in the same, and it cancels out in this difference. The next quantity is the natural indirect effect, which is estimated by setting the treatment to the treated value and the mediator to different values. The mediator is set to the value it obtains under treatment and under control. The control is subtracted from the treated, and because the direct effect is the same in both summands, the difference is equal to the indirect effect. So now the arrow from treatment to outcome is dashed, and it cancels out in this subtraction. So all that we are left with is the indirect effect from the mediator to the outcome. Total effect is equal to the sum of the natural direct and the natural indirect effects. Our treatment, cholesterol, is continuous, and recall that we divided the raw values by 10. Therefore, our effect estimates correspond to a 10-unit increase in cholesterol. Because our outcome is binary, PROC CAUSALMED fit a logistic regression model and presents both odds ratios and the relative risks. Because our data were generated prospectively and have not been oversampled, we could use the relative risks. So we look at the relative risk results. A 10-unit increase in cholesterol directly causes an increase of 6.87% in the risk of coronary heart disease within 5 years. It indirectly causes an additional increase of 1.39% via blood pressure status. So the total effect is 8.26% increase in the risk of CHD within 5 years. The percent of the total effect due to mediation is 16.88% and is also provided in the output. These estimates were produced at the mean values of the covariates. There are other values presented here. We won't go through all of them, but they are explained in the examples in the SAS help documentation for PROC CAUSALMED. Now recall that we requested additional estimates for subpopulations of those smoking 3 packs per day at mean MRW. The estimates did not change, so smoking more cigarettes does not impact the effect, whether direct or indirect, of cholesterol on CHD. But we have to be careful because this does not mean that smoking does not affect CHD. To answer that question, we need a separate analysis. So we can change our PROC CAUSALMED step to analyze smoking. And note on the model statement, we have the outcome, CHD 5YR equals smoking and blood pressure status. The mediator, blood pressure status equals smoking, is on the mediator statement. And the only covariate for which we need to adjust is age at start. And recall that again was identified by PROC CAUSALGRAPH. And here's the results for our smoking analysis, and it appears that smoking has a small but significant direct effect, but there is no indirect effect. Another tool in our toolbox is the CAUSALTRT procedure. PROC CAUSALTRT estimates average treatment effect, recall ATE, or average treatment effect of the treated, ATT, for analyses in which treatment is binary. So the treatment has to be binary. PROC CAUSALTRT fits one or both of 2 models, a model of treatment assignment. We discussed that under potential outcomes analyses earlier, or a model of the outcome, which we have been doing with PROC CAUSALMED. The model of the treatment assignment estimates the propensity scores. Recall from our earlier discussion that the propensity scores are probabilities of being assigned to the treatment group given a set of covariates. And they are estimated usually by logistic regression by specifying the binary treatment indicator as the response and the covariates as predictor. Those covariates, again, are the confounders identified by PROC CAUSALGRAPH. We also learned that you can conduct a weighted analysis using those propensity scores. PROC CAUSALTRT can fit both of those models at the same time and produce robust estimates of causal effects. Here's the syntax for the PROC CAUSALTRT statements. A comprehensive discussion of all the capabilities of CAUSALTRT is well beyond the scope of this presentation. So I encourage you to review the CAUSALTRT documentation and the examples to learn all of the features. There's also a 2017 SAS Global Forum paper by Michael Lamb and Jung for see that paper for an introduction to CAUSALTRT. You specify categorical model and PS model inputs on the class statement. We can use the options REF or ref equals as in other procedures, and we specify the model of the outcome using the model statement. If the outcome is binary, you can use the ref equals option with the outcome variable to specify which level is modeled. You also have options like dist equals and link equals to control the generalized linear model that you fit. Specify the model treatment for the treatment on the PS model statement. PS stands for propensity score. You are specifying the model to estimate the probability of someone receiving the treatment. This should include all pre-treatment baseline factors that you believe are confoundings, and you can use the set that's been identified by PROC CAUSALGRAPH. The 2 models don't have to be the same. However, you do need to identify both the treatment and outcome variables. You can specify the either statement without input variables. That is, to the right of the equal sign, there's no variables listed. For example, to specify a treatment variable without fitting the propensity score model, you specify the treatment variable on the PS model statement, but don't list any variables to the right of the equal sign. There's different estimation methods available, and you specify the estimation method on the PROC CAUSALTRT statement. If both models are specified, then the AIPW is used by default. If only the outcome model is specified, the adjusted reg, REG-ADJ, is used by default. And if only the treatment model is specified, the inverse probability weighted method is used, IPWR. If neither model is specified, then the reg adjusted is used. Now, the AIPW and IPW reg combine estimates from both the propensity score and the regression models to estimate your average treatment effect. These methods are called doubly robust because you obtain unbiased estimates of ATE, even if one of the models, treatment or outcome, is misspecified. So it's a good choice if you can use the robust estimation. It is recommended you do so. Here's our PROC CAUSALTRT step using the same data set, the heart data set. In choosing which covariates you include in the model, recall that you need to satisfy the assumption that treatment assignment and outcome are independent. Conditional independence is satisfied if you adjust for all the confounders, that is, the factors that impact both the treatment and the outcome. Now, this adjustment set, again, was identified with PROC CAUSALGRAPH. If the graphical model that we specified in PROC CAUSALGRAPH is an accurate representation of the data generating process, and we specify the adjustment set on both the model and PS model statements, then we satisfy this independence assumption. Suppose we want to estimate ATE for blood pressure status. Recall from our PROC CAUSALGRAPH analysis that a valid minimal adjustment set contains cholesterol and smoking. We specify cholesterol and smoking as inputs in both the model for treatment assignment on the PS model statement and model of the outcome on the model statement. The P all option on the PROC CAUSALTRT statement requests all output tables, some of which are not displayed by default, but we're not going to go through all of them. Again, review the model information table. Make sure your model was coded as you intended. And the analysis of causal effect table is the main output table and is produced by default even if P all is not specified on the PROC statement. And this table shows the population mean outcome for each level of the binary treatment variable. The ATE is the difference. It is important to keep in mind that the ATE is not derived from model parameters. It is a difference of mean predictions. In statistical speak, you could say it's the difference of y hats. So if you venture into using other SAS stat procedures, regression procedures to estimate causal effects, you have to do so by differencing y hats rather than model parameters as we would normally do. So the ATE in this case is in the bottom row, 0.03321. Okay, in closing, everything we talked about hinges on these graphical models. These visual depictions of our models with the dependencies stated and with missing arrows, independence, are at the key to properly coding PROC CAUSALGRAPH. PROC CAUSALGRAPH will give us the adjustment set that we need to use as covariates in PROC CAUSALMED and PROC CAUSALTRT or other regression procedures. And I thank you for tuning in today to get an introduction into these procedures and modeling causal effects. Thank you.
Great, welcome back. Thanks, John. I've been monitoring the chat during the presentation, kind of collated some of these questions that I'd like you to answer live with the audience here. The first one came from Derek. It was fairly early in the presentation where he was talking about or asked the question about the difference between Sutva and independence.
Sure, Scott, thank you. And I was monitoring the chat as well. I apologize for not being able to answer during the chat. YouTube wouldn't let me respond to the chat. I guess I have to set up a channel. So we'll get through the questions during this session. Independence really is with respect to the relationship between outcomes of individuals. For example, John's outcome is independent from Scott's outcome in some model. SITVA is a little different. John's treatment assignment would not impact Scott's outcome. So it's one individual's treatment assignment not interfering with another individual's outcome. In fact, sometimes this assumption is, there's two parts to SITVA, and the one part is called non-interference. And it means that my treatment assignment does not affect Scott's outcome. The other part two to SITVA is that there's no variability in the treatment assignments or the outcomes. And really the two of them together, I interpret it to the question, have we identified all the potential outcomes? If my treatment assignment changes Scott's outcome, then he has possibly more than two potential outcomes, and our model might have to get quite a bit more complicated, which is possible, but I haven't delved that deeply into this to that extent yet.
Great, thanks for that detailed explanation. The next question was, if you saw in the chat, was this exchange between Laura and Banu about the structural equation modeling.
Yes.
If you can read that and address that, please. Thanks.
Yeah, and Banu is right, because the latent variables are unmeasured, then you would specify them as unmeasured in your PROC causal graph. It's important to put them in there because PROC causal graph might come back and say that the cause and effect of interest cannot be identified, which means there is no valid adjustment set, and that might be because one of the variables that would need to be in your adjustment set is unmeasured. I find you might question, well, okay, what's the usefulness of identifying unmeasured variables? But keep in mind that causal graph doesn't require an input data set, which means you could formulate your model graphically before you collect any data, just to figure out what data you need to collect. And if you find out there's a difficult to measure variable that appears in your adjustment sets, you might have some homework to do before you start collecting data. And there was another response about to this, that yes, SEMs, they estimate every effect. Causal graph is more focused to identify adjustment sets for a causal analysis with, say, CAUSALMED or CAUSALTRT, where the focus is on the y-hats, the outcomes, the difference of the outcomes, which in all the slides where we went through direct effect, indirect effect, total effects, it concerns the y-hats rather than the parameters themselves. So that's another difference, is the focus is on the outcomes rather than estimating parameters.
Great, thank you. I'm looking here the chat. Oh, real quick, just a note, sometimes the YouTube channel blocks URLs, so I pasted the direct URL for John's paper. And if you didn't get that, please visit communities.sas.com to get all the papers on SAS Global Forum 2021. And John's made his paper available as a Jupyter notebook, so a really cool way of interacting with code. If you open that notebook, you can play with code and run it real time, which is, I think, a great addition to a lot of the SAS papers, the contributed papers that are being submitted this year. So a quick note on that. Then we had a question about from Edison about do these models in CausalTRT, CausalMed, do they work on longitudinal data?
Yeah. It's an excellent question. And it requires, from my perspective, it requires more thought, because I think the answer might be both yes and no. No, they do not estimate repeated measures as other SAS procedures do, taking into account all the intermediate data. And I would have to think about this for each analysis case by case, but you can still do a causal analysis from baseline to the final outcome of interest. But if you would have to be very careful in your model. Recall my graph, my DAG, where I showed a collider, and the colliders appear after the outcome. And when you have intermediate data beyond baseline, then you may be in danger of encountering some colliders. So you'd have to be careful. I know there is research in causal models with longitudinal data, and I believe some folks are looking at the ability to conduct these analyses as slices in time, or call them snapshots in time. So I don't have a clear answer to that question. It's a great question.
Okay. Going back, I had a question actually going back, and I think you answered it way early in the presentation about the distribution of variables. Could you elaborate a little bit about that on accounting for that distribution and correlation between covariates?
Okay, so the relationship between the variables that, yes, when CausalGraph identifies adjustment sets, again, there's no data used. It just identifies which variables are the confounders that you need to adjust for. It doesn't not take into account the relationship between those variables. For example, and if you were to do a mediation analysis, the mediator on the outcome, whether it's a curvilinear relationship or accounting for covariates, nonlinear relationships or interactions. Don't ignore your good modeling practices when you conduct these analyses or fit these models. There are capabilities that I did not discuss in the presentation for incorporating interactions in your models. You could include polynomial terms to account for curvilinear relationships. So please don't ignore that. That's what I was trying to say with that slide.
Okay, thanks. Later, one of the last things you touched upon was propensity score modeling, which is something I've used in the past, and a great way of with that quasi randomization technique. Could you explain a little bit about the PS model versus the model statement on some of the limitations and what to include in each of those variables? I know you got the left and the right-hand side of the equation on both of those model statements.
Sure. So it's an interesting procedure. If you recall earlier in my presentation, I said you could have a randomized controlled experiment, and a randomization balances covariate distributions across treatment groups and no confounding. You could model the treatment, that's the propensity score models, or you could model the outcome, the structural causal models that I focused on. CausalTRT can fit both a model for the treatment with the PS model statement and the model of the outcome with the model statement. If you do both, as we did in the example, then you get some robust estimates. And one of your models might not be correct, but because the estimates are robust, it protects you against misspecification. But you have to specify both of those statements, even if you're only fitting the treatment or the outcome. It's with those statements, for example, PS model statement, you use to identify to CausalTRT the treatment variable. Even if you're not fitting the model, you specify the variable and then just a semicolon. No equal sign, no variables after the equal sign. Same goes for the model statement. It's on the model statement that you specify the outcome variable. If you're only fitting the model for the treatment, you still use the model statement, specify the outcome variable and a semicolon. No equal sign, no inputs after the equal sign.
Oh, great. Great, thank you. Monitoring the chat, I've seen a lot of compliments So thanks, John. I know
That's good.
this content, you can make probably a half-day class out of all the content. So
At least,
it's great
yes.
that you put it all in 1 hour, which is definitely a tough squeeze. So thank you for joining us today to answer these questions. Do you have any kind of final thoughts, or maybe I've missed something in the chat that you
No, I'll just reiterate,
found?
please visit my paper on SAS communities. It's the first time I've ever done anything in a Jupyter notebook, very steep learning curve. But it's quite cool that you can play with the code that you saw in my presentation. It is available. You can alter it, rerun it as you read the paper. Happy to receive feedback and questions. My email is in that paper, so feel free to contact me directly.
Okay, thank you one last time. And for everyone else, we hope that you'll continue to explore all the other great content that we have available in the SAS Global Forums YouTube channel. And don't forget to take the session survey on the SAS Global Forum Attendee Hub. All right, goodbye.
Thanks, Scott.